Welcome to the lecture 4 on the renewable energy sources and applications. Myself Dr. Saradindu Panda. The today's topic is the characteristics equation and the efficiency of the solar cell. From the equivalent circuit, it is evident that the current produced by the solar cell is equal to that produced by the current source minus that which flows through the diode minus that which flows through the shunt resistor. This is the equivalent circuit. This is the load current. This is the diode current, and this is the shunt current. So the I plus ISH plus ID is equal to the IL. So from this we can write I is equal to IL minus ID minus ISH, where IL is the photo generated current, I is the output current, ID is the diode current, and ISH is the shunt current. The current through these elements is governed by the voltage across them, that is Vj is equal to V plus I into Rs, where Rs is the series resistance, I is the total output current, V is the voltage across the output terminal, that is V, and Vj is the voltage across the both diode and the shunt resistance Rs. By the Shockley diode equation, the current diverted through the diode is ID is equal to I0 into e to the power of Vj by nVt minus 1. We all know that. Where I0 is the reverse saturation current, N is the diode ideality factor, normally in ideal case that is 1. Q is the elementary charge, K is the Boltzmann constant, T is the absolute temperature, and Vt is equal to the Kt by Q, that is thermal voltage. That value of this is 0.026 volt at the 25 degree centigrade. By Ohm's law, the current diverted through the shunt resistor, that is ISH, is the Vj by RSH, where RSH is the shunt resistance. Now if we put the value on ID and ISH in the total current equation, then we will get the I is equal to IL minus ID, that means I0 to the power of V plus IRS by NVT minus 1, minus of ISH, that is V plus IRS by RSH. Now come to the open circuit voltage. When the cell is operated at open circuit, I is equal to 0 and the maximum voltage across the output terminals is defined as the open circuit voltage. This is called the open circuit voltage, where the I is equal to 0 and V is the maximum. The red line denotes in the curve in the picture, that is IV curve of the solar cell, and the blue line is the power curve of the solar cell. Assuming the shunt resistance is high enough to neglect the final term of the characteristics equation, then the open circuit voltage come out as VOC is approximately NKT by Q ln IL by I0 plus 1. IL is the load current. The open circuit voltage corresponds to the amount of the forward bias on the solar cell due to the bias of the solar cell junction with the light generated current. Now the VOC can also be determined from the carrier concentration, where it is expressed as VOC is equal to KT by Q ln Na plus delta N into delta N by Ni square, where KT by Q is the thermal voltage 0.026 volt at 25 degree centigrade, Na is the doping concentration, delta N is the excess carrier concentration, and Ni is the intrinsic carrier concentration. The above equation might indicate that the VOC goes up linearly with the temperature. However, this is not the case, as the I0 increases rapidly with the temperature primarily due to the change in the intrinsic carrier concentration Ni. The above equation shows that the VOC depends on the saturation current of the solar cell and the light generated current. While the ISC typically has a small variation, the key effect is the saturation current, since this may vary by the orders of magnitude. The saturation current I0 depends on the recombination of the solar cell. VOC is then a measure of the amount of recombination in the device also. Similarly, when the cell is operated at the short circuit, that is V is equal to 0, the current I through the terminals is defined as the short circuit current, that is the maximum current, that is the ISC. The ISC is the maximum current from the solar cell and occurs when the voltage across the device is 0. It can be shown that for a high quality solar cell, where the low RS and the I0 and the high shunt resistance, the short circuit current is approximately equal to the load current. Now, the short circuit current depends on a number of factors which are described below. The area of the solar cell. To remove the dependence of the solar cell area, it is more common to list the short circuit current density, that is JSC, in milliampere per centimeter square, rather than the short circuit current. The number of photons. The short circuit current from a solar cell is directly dependent on the light intensity, as discussed in the effect of the light intensity on the current. The spectrum of the incident light. For most solar cell measurement, the spectrum is standardized to the AM 1.5 spectrum. The optical properties. The absorption and the reflection of the solar cell. The collection probability of the solar cell, which depends chiefly on the surface passivation and the minority carrier lifetime in the base. Now come to the very important parameters of the solar cell, that is efficiency. The efficiency is defined as the ratio of energy output from the solar cell to the input energy from the sun. The efficiency of a solar cell is determined as the fraction of the incident power which is converted to the electricity and is defined as the P maximum is equal to the open circuit voltage, short circuit current and the fill factor, the multiplication of this. And the efficiency is equal to the maximum power, that is P max, VOC, ISC and fill factor multiplication with respect to the P in, the input power of the solar cell. The input power for the efficiency calculation is 1 kilowatt per meter square or 100 milliwatt per centimeter square. Thus, the input power for a 100 cross 100 millimeter square solar cell size is 10 watt, and for the 156 cross 156 millimeter square solar cell is 24.3 watt. This is the standard input power for the efficiency calculation. Now these are the references. You will go through it. Thank you.